Okay, everybody, let's get started. Welcome back to System Software. Hooray, yes. I think the ones that are here are very excited to be here, or have nowhere else to be, perhaps. Okay, so we wrapped up our discussion about functions last time, how they're implemented, how they're type checked, how to generate code for them, and the project won't start for Project 4. Officially won't start until Thursday when Project 3 is due. So just as a reminder, Project 3 is due in 2 days at 7:30. The Project 2 regrading deadline, I think, was today as well. So if you wanted 1 point off instead of 2 points off, some people came to office hours for regrading. So Project 3 is due soon. And then on to the last and final project before we wrap up the semester. Just to show you where we are, we've now begun the last kind of 4 lectures that have content before we start doing review. And the rest of the class is stuff you won't have to actually implement in your project. This is more like advanced topics in compilers and program analysis. So it'll be just kind of a little bit of simple homework, some knowledge stuff, and a little bit on the exam. And don't worry, there'll be plenty of review for the exam. And originally, I wanted the project to be due, well before the exam, but we had a storm in the beginning of the semester. Project 4 got pushed back a little bit. Project 4 is due in the same week as the exam, but we'll have 2 lectures of review and the break. So for this week, we're going to cover optimizations. We'll talk about what that is today. I've borrowed some slides from another course, which we'll use for that, since it's not specific to Simple C. But before we get started, questions on Project 3, questions on Project 4, although the test cases aren't out for Project 4 yet, but any questions from the last lecture, from generating functions? What are your questions? Everybody's in good shape, I guess? More or less? You have 2 days to figure out if you're in good shape, I guess? Okay. Okay, so that's the,
With the test case, or with the Project 3, should we put consideration if for something like, say, not expression?
Well, yeah, if you look at the grammar, the not this, well, this would be a factor in your grammar that respects order of operations. But you see, not is before not a number, but it's before an expression. So this expression may expand to another not followed by an expression. So you could have an infinite or an arbitrarily long sequence of nots. Does that answer your question? Yeah. So just like, it's just like the binary operators, except it happens to be unary. It only takes one operand. But the same nesting applies. Questions? What are your questions? Okay. So let's get started on some of the fun stuff. So all the topics we covered in the last, pretty much for the whole semester are pretty classic parts of the compiler. Parsing is mostly a solved problem, although there's still some parsing work that gets eked out, including some of mine in grad school. But largely, a lot of the compiler research, after all the basics of front-end analysis and code generation, was on compiler optimization. So the goal of optimization, as some of you have noticed, the code that I guided you to generate would be, it's kind of boneheaded if a human wrote it. Storing and reading from memory from the same memory location, one line after another, or having additional branches that you don't need, not considering whether a branch is true or false and can never be true or false. And so when you do this nice kind of naive code generation algorithm, it's very easy to write, but the code you get could be better, could be faster. And one of the benefits of having a compiled language is that it obviates the need to handwrite assembly. But if the assembly doesn't perform very well, then developers may want to continue to program in assembly. And this is actually still the case for, say, graphics programming or programming for specialized hardware, or when you need very, very high performance and your compiler just won't cut it. But in many, many cases, the compiler can outperform kind of novice assembly programmers. And the way this is possible is through a whole series of different kinds of kind of heuristic optimizations. So the idea is to improve the performance of the IR by taking better advantage of the computing resources you have. So, for instance, everyone knows that reading RAM and reading disk is way slower than moving values between registers. You should all know that from architecture. So if we can exploit some of that knowledge when we generate code, then we can make code that performs better, even though it's doing the exact same thing. And as this slide points out, it's a very active area of research. The LLVM compiler people are still doing a lot of work on compiler optimization, and I can show point you to some blog posts later about that. And at this school, there's a whole class dedicated to just optimization. Okay, so why can we do optimization? I kind of hinted at this in the beginning, but when you do this IR generation in a naive way, you get a lot of kind of redundancy. You may try to compute the same expression multiple times. Well, you wouldn't have to do that if you save the value. Programmers may want to write. I think it's a little unfair to say programmers are lazy, because sometimes it's better to have code that's easier to read than performant. And if you can kind of bridge this gap with the compiler to make
programming exists because we just don't want to do it ourselves. Write it once and save yourself 500,000 times you have to do it again.
Well, yeah, that's another argument, that the compiler is kind of the repository for performance hacks. That's kind of one. That's an interesting way of looking at it. But yeah, I prefer writing code, C code, and letting, or high-level language code, and letting the compiler kind of do the sort of mind-numbing optimizations for me. And that's what these optimizations can do. So to give some intuition, let's take a look at this program on the left. So this is going to be slightly different language, although it's very close to simple C. This is what some IR could look like. This is somewhat close to what LLVM IR would look like. So if you're doing project 3 or project 2 or even project 1, this should look fairly familiar. If we've got some expression on the right-hand side that needs to be broken down into its individual CPU operations, its individual architecture operations. So that's why we've got a couple operations here. And for each of these C language statements on the left, we've got our equivalent IR expressions on the right, or statements on the right. Questions on this? Do you want to digest this for a second? Is it pretty straightforward? So notice that in this case, we've got some redundancy here in our IR. We're computing the same thing in two different places. And you'll notice that in certain programs that you write, that you compile for simple C, you'll probably notice the same thing if you're looking at the LLVM IR really closely. So one optimization we can do is to just remove this redundancy. So notice here that we're doing, so X is, where is this? Oh yeah, right. Sorry, I was confused about the parenthetical. So X plus X is the common operation that we can replace here. So T0 is already X plus X. So rather than recomputing it every time we need it, the compiler and modern compilers are smart enough to do this, where they will keep track of what expressions have been computed already and just reuse the same register. So questions on this? Pretty straightforward, right? Something that you can do by hand, even in C. So another observation is that if we look at this program, now that you've actually seen how while loops are implemented, you know that this expression is evaluated every time you run the loop. So even though us as a programmer, we kind of think as the body as the only thing that's being iterated, and when you actually write a compiler for LLVM or for a machine, that kind of quickly disabuses you of that notion that this condition is just evaluated once. It's evaluated every time you do the loop. But notice that Y and Z aren't actually changed by the loop. So even though our kind of straightforward compilation of a while loop would always recompute everything, all parts of the conditional expression, there's really no need to recompute Y plus Z because it never changes in the loop. So with that observation, we can move that outside of the loop. And that's another big area of optimization in compilers is this, taking invariants out of the loop. Things that never change in the loop, there's no need to recompute them every time. So just, compute them once before you enter the loop. Okay, so this is kind of a good point that optimization in like the mathematical sense is finding like the best solution. But in general, for compilers, it's not possible to always, for every possible program, generate always the optimal solution. So you can kind of think of compiler optimizations as like improvement or performance improvements. It also depends on what you're trying to optimize. You may not always want to optimize for performance. So a good optimization should not actually change what the program does, the observable behavior. You could think of this as the functional equivalence. If you give it the same inputs, it should have the same outputs. That's how we're testing your program. And in fact, for some work that I'm working on in side channel attacks, we actually don't want the compiler to introduce security vulnerabilities that have nothing to do with the functional equivalence. So modern compilers worry just about functional equivalence, more or less. But there actually are other cases where the constraints on your optimization would be more than just input-output equivalence. There'd be other observables about the program that you'd want to make sure are preserved or not changed by the compiler. It should produce IR that's efficient, and ideally the compiler is not going to take 5 weeks to run to produce your program. It turns out in practice that even good compilers do sometimes introduce bugs. So the compiler is still a piece of software that's still human developers who can make mistakes. And there is actually research on formally verifying compiler optimizations that came out in the past several years. Really good work. If you're interested in any of the kind of research topics I mentioned, let me know and I can point you to papers. And optimizations can sometimes just miss simple optimizations because a lot of this is very heuristic. What order do you do the optimizations in? Which ones do you apply? Which ones do you not apply? And so almost all of these optimizations are either NP hard, they're really, really slow to compute, or they're just undecidable to figure, that you need too much precise information about the program to actually perform the optimization you want to perform. Okay. So I touched on this a little bit. What are we trying to optimize? So this really depends on what you need as a developer. So usually we think of optimization as improving performance, but that's not the whole story. If you're writing for, say, a very resource-constrained device, then maybe memory is more important to you. Maybe power usage is more important to you. So optimization, you have to pick what it is you're trying to optimize. Okay, so we generate IR, LLVM IR, and the LLVM library behind the scenes will turn that into machine code, like x86 or ARM machine code. And this actually provides multiple opportunities to do optimization. So as you noticed in your own code output, there are plenty of optimizations at the LLVM level that you could do, like for instance, replacing division by shifts, division by 2 by shifting, or multiplication by 2 by shifting. There's definitely optimizations you can do at the LLVM IR level, and that's really convenient because you only have to write those optimizations once. You don't have to repurpose them for every machine that you're targeting. But there are optimizations that are also based on the performance of the machine. So for instance, in the Intel world, Intel has these special purpose registers that are used in only certain instructions. And so certain additions and certain operations, I can't remember what they are, but certain operations use specific registers and are actually more performant than using other registers. Whereas RISC architectures, all the registers may be treated the same and you don't have the same opportunities for machine code optimization. So if you look at the LLVM or any modern compiler, there's probably going to be at least two places where you have optimization. One at the IR level. All modern compilers these days have, all the popular ones have an IR, and also at the machine code level after machine code is generated. And as this points out, some optimizations are somewhere in between. So, replacing some floating point multiplication here with division may be done at the LLVM IR level, maybe done at the machine code level. So ignore these days, but we're really just gonna cover. Today actually we are gonna cover local optimizations. The next time we'll cover global optimizations and hopefully get to register allocation. But let me talk about what all that is. Okay, so in order to actually optimize the program, the compiler has to actually be able to reason about the properties of that program. Like, is this value of x always positive? Is this x always a constant at this point in the program? And we need to make sure, because we want these optimizations to not change the behavior of the program, we need to make sure that these analyses are sound, which means if our analysis says something about the program that is actually true in the real program. That may seem almost like obvious, right? But when you have a program where the values can change almost arbitrarily and you have complex loops, complex state changes, this is not exactly so simple to get this soundness right. Because certainly you can optimize it for one input to the program or two inputs to the program. But to do this for all possible inputs to a program that has millions of lines of code is not necessarily so straightforward. And all the analysis we discussed in this class are sound. The slides ask why. I kind of answered that question already. But can anybody think of a counterexample? Like, when would you actually want to have an optimization that is not sound, where maybe it's specialized to certain inputs to the program, or is that just kind of ridiculous?
There's always something.
There's always something, yeah. But are there any cases? Well, there is a line of work called
that weird calculator where it's like you run your question in and it always gives you the wrong answer.
Okay,
there is such a thing.
But if it always gives you the wrong answer, isn't that the functional specification of it? So it's just has a different meaning for the language. Well, anyway, I mean there are like there is research on what's it called, partial evaluation, where you actually specialize a program to a particular set of inputs, and it does have applications in the real world to actually do that. But here we're looking at cases where we don't know what the inputs are, and we try to optimize for all possible inputs to the program. So here's a point for here's just sort of a little intuition behind soundness. So some sound properties about X that a compiler could figure out here. So for instance, what are some unsound properties? What if the compiler just assumed X was always 42? What would happen if we try to optimize around that? Well, yeah, it would be bad because we're not accounting for the fact that Y could be less than 5 and X might be a different value. So it's sound in our model of the program to say, well, X holds some integer value. So that's something that, if it's true in the analysis, then it's true at in all possible inputs to the program. Yeah.
So in this program, X would always be a garbage value, right? So like, would our compiler try to yell at us?
Well,
like,
what do you mean a garbage? Do you mean Y?
Because Y is never initialized, so Y will be a garbage, and like Y will never be less than 5, and we'll just get to try to print X where X is never been initialized.
Okay. So your classmate's pointing out that Y is never initialized here. So that's probably just an omission here. It's kind of assuming that it's read in. But strictly speaking, the C standard is kind of undefined behavior for Y. So if you actually run this, it could be 0. It could be some garbage data.
It could be garbage.
But yeah, the point here is that we don't know what Y. If we don't know what Y is, if we treat it as an input to the program, that is kind of an oversight in these slides. But if we treat it as an input to the program, then X just can have multiple possible values. So what can we do for all possible values of X? So we can't specialize it to 42 without, being wrong about some inputs to the program. That's really just the point about soundness. So we could also just in the compiler say, well, we know it's either 137 or 42. So we could do that. We could do that for all possible variables, kind of, right? What would be wrong with that though, if we track every possible concrete value? Can anybody see a possible downside to doing that?
How many possible concrete complete values are there.
Well, yeah, if you have a loop that's, say, based on an input value, yeah, it'd be pretty hard to track all possible. I mean, the state could, conceptually be infinite, or at least, the size of a maximum integer. And then, basically the power set of all possible subsets of combinations of integer values. So your state can explode. The state of the compiler trying to track the possible runtime states could just blow up massively. So the compiler, well, at least the compiler optimizations we'll talk about today, don't try to track all possible states to x. So it'll just say something like x is an integer. And in fact, part of the reason why type checking can actually help during compilation is that the program already told you what the types are, and our type checker can prove for every expression what the results of those expressions are. So yeah, and this is the case where it's unsound for all possible inputs. Yeah.
So one way you could improve this would be you could check if you only have one initialization of x, and then you know that x never changes.
Yeah, that's a good point. So if you can, yeah, that's a really good point. And actually, this is getting to some of the analyses that the compiler does. It'll actually check where is x defined, where is it used, and it'll use that information to do certain optimizations. That's a really good observation. So here's a weird one. At this point in the program, x is either 137, 42, or 271. So is this sound? Well, okay. So who says yes? Who says no? This is like a really subtle point in soundness. So I always mix this up. So I'm just going to look up soundness in Wikipedia. But soundness is it's like an if statement that only goes in one direction. Like the truth table for if statements, A implies B. So it only goes one direction. So, how does it go? Yeah, so if it's true in the model, in the compiler, then it's true at runtime. That's the soundness argument. So it doesn't have to be true in the model, actually. Right? It only has to be true in the model if it's true at runtime. So if it's false at runtime, then it could be false at. So this always confuses me. There's this duel of soundness and completeness. Soundness is like if A then B. Completeness is if B then A. But I'll leave you to look it up because this always confuses me. But it's basically one directional. If your model says it's true, then it should be true at runtime for soundness. But go ahead and look that up yourself. But yeah, so basically you can kind of over approximate what the values will be at runtime and still be true about what they are at runtime. Because if you do some operation assuming assuming that there are more possible values, you'll still be right at runtime. So if we assume x is any of these three, it's still true at runtime because it's only 137 and 142. Yeah. With that logic, wouldn't that mean that assuming x is any number would be sound? Exactly right. So the first one, if you just assume x is any integer, also sound. It's not always, it's not every possible integer at runtime, but it's still sound. So this is like some deep stuff in math logic about So take a math class on math logic and learn more about that, and then you can come tell me about it. Okay. So we also want to make sure that the optimization preserves the semantics of the program. And this, I think, is a little bit debatable. So saying that you shouldn't, replacing bubble sort with quick sort is not preserving the semantics. It's kind of arguable. It depends on how you want to define your language. But yeah, I think, yeah. So basically, in this class, we're going to, preserve the semantics of the language. Yeah. It's like the meaning of the expressions in the language. It's like the meaning of the expressions of the language. Yeah, it's like you have to define what the program computes in some rigorous way, and just prove that the optimization doesn't alter that. So semantics is another kind of touchy topic. There are very, very precise ways to define this, but we'll just say that the optimization is not going to alter the meaning of the original program. So it's not going to replace quicksort with bubble sort. So at a kind of high level specification of the program, it's the same, but the actual implementation of it is different. So the semantics of the program are not changed. Anyway, got a hand wave over that a little bit. If you're interested in that, I can point you to some resources for program semantics. There are lots of ways to define the semantics of a program or of a programming language. Okay, so this slide is kind of pointing out that at each stage of our compiler, we're using a new kind of abstraction. So, scanning is regular expressions, parsing is context-free grammars. Our type checking was using what are effectively proof systems and symbol tables. For IR generation, although you didn't have to make an explicit AST, you effectively had a syntax tree when you're doing recursive descent. And so for optimization, we need some other formalism that's going to capture the runtime behavior of the program in a way that's going to make it possible to analyze. So this structure, which I've shown you before, is the control flow graph. So just as a little review, the control flow graph, I think this is also talked about on the next slide. Control flow graph has basic blocks, which are straight line code that doesn't have any branches in or out. And the edges of this graph are the branching behavior. So if we've got this is our label here. That's our label for this green code. This is our straight line code for the red code. We've got some branch statement here at the end of the green. And this will either not branch, go to the blue section, or it will branch and go to this gray section. We've got an unconditional branch here at the bottom of our blue section that takes us back to L0. So even though this code here is, there's no branching out of this code, there's a branch into the code. So so that way each basic block can just be pure straight line code without any branches in or out. So questions on this? We sort of talked about this a little bit, right? And there are algorithms for actually constructing this automatically. And as I mentioned before, you can kind of use this control flow graph to start decompiling the program to some degree, because it recovers the original structure of the program. So you can even, if you're familiar with these control flow graphs, you can just see that, okay, this is obviously an if statement. I've got a back edge. That must be a while loop of some kind. Or, well, I guess, this together is just a while loop. Okay, so basic block sequence of IR instructions, no branches in or out. This is the control flow graph. I think we pretty much covered this. Okay. So there's local optimizations that you can do at different levels of your code. So if we only work in a single basic block, no branches in or out, then these are local optimizations. They're global if they work on an entire control flow graph, and it's interprocedural if it works across multiple functions. So each function has its own control flow graph. If you can do your optimizations across those functions, which may be thousands and thousands of functions, it's an interprocedural optimization. And so, interprocedural optimizations are way more complicated. We'll just talk about local and try to get to some global optimizations as well next time. Okay, so let's take a look at some local optimizations that can be done within basic blocks. Make this a little bigger. So we can see here that T0 is set to some constant, and then Y is set to T0. So can we just substitute T0 for, can we just substitute 137 for Y here? Is that safe to do?
What do you mean?
Well, can we do this, where we just take the value of T0, since we know it's a constant, and just substitute it for Y? Is that safe to do? I think you think I'm tricking you.
Assuming that 137 is like an int, then I can't see why not.
Yeah,
137. We might as well, because when you look at it, the only thing that Y ever is 137.
Yeah, that's a good point. So notice that the only thing T0 is never used anywhere else. Y is never used anywhere else. So there's no reason we couldn't do this. This local composition. I wasn't trying to trick you. I was just saying, making sure it was okay with you guys to do that. So similarly, and this is kind of reflects in your simple C code generator. This is like, the step that loads from memory. You can think of it like that, where you load from memory and then you set it to some register. And there are places, depends on whether you're doing LLVM IR or machine code, but there are, anytime you have these temporary variables that are only set once and only used once, you can certainly just replace them. Yeah.
So, I don't have a certain code for this code channel, but I thought in LLVM IR that you had to store, or I had to load it and then store. Is there, so there's no way around that, or you're saying that there is a way?
I was just saying that. Yeah, that's a good point. Yeah, that's right. So you will have to load it into a register, but if you're doing some other movements of that register later, then you may be able to elide those. LLVM is kind of a special case because it only allows variables to be assigned once, and it actually does that because it makes certain optimizations easier. So this is more like, this is just an example. Think of these as like registers in a machine, for instance. Yeah.
So it's like if we were doing this in LLVM, since we would have to do the load to get the value of y,
Yeah.
would it just be something like, because y's value never changes, we just use that to loaded value every single time instead of loading it every time we see y?
Yeah, right. Yeah, that's right. So you wouldn't load it multiple times. That's the register allocation problem. We'll talk about that hopefully next time. It's sort of hard to tie this to LLVM because LLVM doesn't allow just assignments of registers to other registers. Think of this more at the machine code level where you're moving between multiple registers, for instance, or if your IR is not like LLVM where you only allow a single assignment per variable. So yeah, or you can think of this at the source level, for instance, if this is for some reason happening at the source code level. And as your classmate pointed out, we know that y is always 137, so those could also be replaced for y. There's no point in even storing a value to y if we know that y is always constant. Okay, so we'll look at that a little more, those optimizations at the global level. But let's take a look at our first local optimization called common subexpression elimination. So notice here on the left that we've got a plus b multiple times in our program. So now if you were thinking, oh, I'm really clever, I'm going to take away, make this optimal, rewrite the code, add a new variable, the compiler can actually already do that. The compiler can keep track of all the expressions that are being computed and make sure that they're only computed once and just use the result wherever the second or third use of that expression is. So there's lots of wrinkles to doing this that I think you can probably imagine. Can anybody think of what problems there might be in doing that? Like when would you not want to do this? Yeah.
What if a changed between
Yeah,
lines?
exactly. So if a changes somewhere in between here, then syntactically the expressions look the same, but semantically they're different. But in this case, they're the same. We can also consider this constant 4 as being the same subexpression, and we can replace that as well. And similarly, and so that opens the door to new subexpression eliminations. So even though there's no corresponding expression in our original source code, when we apply this common subexpression elimination multiple times, it actually creates the opportunity for more optimizations. So real-world compilers may iterate over these optimizations multiple times to try to exploit new optimization opportunities that come up. And then, as far as I understand, these are fairly heuristic techniques for doing this. Like how many times do you iterate? When do you stop? Does it ever make performance worse if you do too many optimizations? Okay, so that's common sub-expression elimination, kind of an overview. Questions about that at all? Questions about this? Yeah.
These are all local.
This is still local, yeah. It can actually be done globally as well. But right now we'll just look at local. Yeah.
So when this is happening, is it like real time, or does it like put out all the code and then look through it afterwards?
Yeah, the code. Yeah. So in LLVM, all of the IR code is going to be like probably in memory, or at least, yeah, you're going to be operating on a structure that holds all of the. Yeah, because like the LLVM style or the style of compilers where you separate the front end from the code generation. Nowadays, maybe you could have done optimization while you're emitting the IR code, but because we all just kind of rely on this common LLVM IR, that's the optimization happens after you generate the LLVM IR. And from I think the LLVM has a structure for the IR control flow graph and one as it generates the machine code. So it's keeping all that in memory and successfully doing the optimizations on that structure. But I'm sure you could probably do some optimization maybe to do that. But as we'll see with the global optimizations, you need some larger view about facts about the program, some properties of the program that involve multiple parts of the program. And so you wouldn't be able to do it kind of locally anymore. This can be done just on one basic block at a time. So you wouldn't have to generate the other basic blocks technically. But if you want to do the more powerful optimizations, you need the whole control flow graph. Yeah.
So when we write our LLVM code, we get the LL file.
Yeah.
And you're not planning on that.
Yeah.
Planning to do the optimizations on that.
Yes. Yeah, it does. It does. Clang will do the optimizations on that. It'll do both optimizations on the IR and also on the machine code that it generates. So behind the scenes, it's running. Yeah, I don't know what it does with common sub-expression elimination. Probably is a little different because it's already IR. Clang could do that like you said, at the front end. You could probably do the common sub-expression elimination. Not sure if LLVM does that. There may be similar performance benefits from other optimizations that it does, but I'm actually not sure. So the kind of definition of it is if we have two variable assignments to the same operation, and like your classmate pointed out, if the values of these things have not changed, then we can rewrite the code like this, where instead of the first sub-expression, we just use v1. Make sense? Questions on this? Okay, so let's look at copy propagation. It's kind of a similar optimization. So notice here on the left that we've got, the first one is x. So x is being, x is set to some new object, so x is being set to some temporary that constructs this object. And then x is used in multiple places. So there's no need to have, two copies of this object. So we can just replace the uses of x with whatever the right-hand side of the assignment of x was. Let's see if there are more here. Oh yeah. So yeah, this is involving like the stack and all kind of, this IR is a little bit different from what we're looking at, but if we just assume that the IR assigns a to some temporary value and a never changes, there's really no point in keeping a around. We can just reuse the right-hand side for a. And this will open the door to future optimizations where we can get rid of the use of a. So and similarly, temp5 is equal to c, and wherever temp5 is used, we can just replace it with the right-hand side of temp5, and so on. So every time you see, so I won't go through all of these, but the idea is if you've got two variables that are equal to each other, or they're an assignment of v1 to v2, then as long as v1 and v2 are not reassigned, you can always rewrite a equals v1 as a equals v2. So the benefit of this, at least in this example, is that it opens the door to further copy propagation optimizations. So eventually, a will just be assigned to 4 instead of going through all these temporary values, and it'll, kind of like constant propagation. This is a more, it'll open the door to more optimizations. Okay, questions on that? Questions on copy propagation? Kind of similar to the to this common sub-expression elimination, but pretty straightforward, right? So dead code elimination is a little more interesting. So here on the left, x is being assigned to some object, new object, a set to 4, c equals a plus b. We're calling some function on x. And so once we performed all of this copy propagation, so if you remember from before, instead of using x, so where was it? Instead of using x, we just used temp1. Well, it left this assignment to x here without x ever being used anywhere. So we can run another optimization that takes a look at the code, and sees, well, are there things being assigned but never used anywhere? And if they are, then we can remove them without hurting without affecting the functional behavior of our original program. So all of these variables here, because we applied this copy propagation, are no longer even used anywhere. Eliminated a whole bunch of stuff. Yeah, eliminated a whole bunch of stuff. Questions on this? Okay, so dead code definition is if variable is assigned, but it's never read anywhere, then you can remove the code. Okay, so just a little comparison of before and after optimization. We've reduced a lot of the operations in this code. Okay, so as I mentioned before, if you want to get a larger effect from these optimizations, you've got to apply them multiple times, because each time you apply one of these optimizations, it opens the door to further applications of the optimization. And I don't know, there may be work on kind of heuristics about how to choose these. I think the LLVM compiler developers work on that a lot. But as far as I understand, it's fairly heuristic. Okay, so, well, this is just going over again. This is just a review of applying local optimization. So here's common sub-expression elimination. We have b and c equal to the same expression, so we can replace the second use of the expression with b. We've got copy propagation, where c is equal to some value b, and c is used. So we have no need to, we can substitute for c its right-hand side, which is b. And then dead code common sub-expression elimination again. And then, well, they didn't show it here, but you would have potentially dead code elimination if C is never used again, depending on what the rest of the code looks like. Some other types of local optimization are instruction. Well, it calls it arithmetic simplification. I think it's also called instruction. Oh my God, I can't remember the name. Weakening or something, where you take certain operations like multiplication by factors of 2 and factors of 2 to the n and replace them with shifts. Constant folding, where you just have the compiler basically interpret constant expressions. And some of you actually asked this for project 1, I think it was, where can't the compiler just compute these values for these constants? And yeah, they totally can, and compilers actually do that. So to just, because this is going back to the soundness stuff, where for every execution of this program that 4 times 5 does indeed equal 20. So you can do that replacement. You can do that computation. Okay, so all right, so I can kind of skip this a little bit, but it turns out that if we want to actually implement these optimizations, there are some program analyses we have to do. So there are 2 analyses we're going to look at for local optimizations. They're called available expressions analysis and liveness analysis. So available expressions captures that intuition we thought about when thinking about when can we actually do this common sub-expression elimination. And it's exactly when the variables in the expression are not changed in between the place where the two versions of that, the two copies of that expression are used. So we want to design a program analysis that'll prove to us for all possible inputs that those common subexpressions are indeed have no intervening assignment statements. And so you can imagine if you have a lot of loops or branching, that can be quite tricky. But today we're just going to look at straight line code, proving that for straight line code. So this is just more about the idea behind the algorithm. If we have a statement A equals B plus C, then any previous expression that we were trying to move forward, that we were trying to eliminate, we invalidate that. We can't move that expression ahead anymore, but that creates a new subexpression that we can try to eliminate in later parts of the code. So the way we do this is we just iterate top down through the code, keeping track of all the expressions that are available. That's why it's available expressions. Keeping track of all the expressions that are available between each statement, invalidating ones that get invalidated by new assignments, and updating new ones each time we see new assignments. Okay, so let me show you an example of this, what this looks like. So we start with the empty set, no available expressions. When we see our first assignment, we just kind of keep track of it. We know that A equals B is an expression that we could, if we find a common use, we can eliminate. When we see C equals B, now we've got two expressions that we could potentially eliminate in future code. When we see this D equals A plus B, nothing that we've seen before has been reassigned. So all of these expressions are going to be still available to us to replace if we see common expressions. Similarly with E, now we've got four expressions that we could potentially replace in future code. But notice when we reassign B, our old expression for D gets removed and the new expression gets added. So finally, when we see F, now we've got this full range of common subexpressions. So notice none of the actual common subexpression replacement has been done. A plus B, maybe there's some opportunity to do common subexpression elimination, but this analysis is just tell me what the available subexpressions are so I can then do my common subexpression elimination. So before we kind of did it intuitively, but if we want to implement this in a compiler, we need a sound analysis, an analysis that's never going to be wrong for any inputs, to tell us where these opportunities for common subexpression elimination are. So questions on this so far? Questions on this? Yeah.
Isn't there a way for a compiler to be like, for example, when I see the last line, it looks like E equals A plus B and F equals A plus B. Isn't there a way E equals F? That way you would save space.
Yeah. So that's exactly the common subexpression elimination. That is what common subexpression elimination is. But the point of this is that in order to actually do the common subexpression elimination, we need to know what the available expressions are at that point. So if, as a human, we might look and say, oh, well, E equals A plus B here, F equals A plus B here. But if we weren't rigorous about this, we may miss an assignment to E in between it. Or, if we wanted to replace A plus B with D, we might sort of do that intuitively, but D is being reassigned. So what this analysis does is it collects at each program point which expressions from before that program point are available to do the common subexpression elimination. And that's needed exactly because D is reassigned, or any of these values can be reassigned. So if A is reassigned, then we have to eject it from this list of available expressions.
All the three other expressions are pretty much the same. A equals
Yeah.
B, C equals B.
Yeah. So the optimization will have to make a choice about which one to apply, and it'll probably have to do this elimination multiple times in order to get some optimal result. But as before, I don't know if this is undecidable, but it's definitely an expensive problem to do. So the optimizer may just make a guess that is less optimal than some other guess that you could make. Yeah. Question.
So there's I guess there's accruing such a big set.
Yeah.
Questions. Can you just update it every time, go
You mean you do the replacement?
Oh, yeah,
Or?
yes, you need replacement.
Yeah. I think in practice these are probably combined. I'm actually not sure, but later we'll show an example of combining the analyses together. I think this is more for like to be pedantic about this is the exact program analysis that we're using. You can certainly combine it with your optimization. So here's the common sub-expression elimination. It's also going to be making like a choice about which. Yeah.
Would you say this is similar to kind of like the bounded free variables in a way, or bounded free expressions like with lambda? Or is it a little different?
It's different because there are no free variables here. There's no like closures happening here.
Yeah. Okay.
Yeah, I think it's a little different. Yeah, I think it's different.
Okay.
Yeah.
So depending on the order of the optimizations that are run, it may get different code outputs.
I think that is the case. Yeah.
So like if you're to
Yeah.
D equals A plus B, or if it were to go, well, D isn't used until 3 is fine. Then it would be used to have E equals D when you do that elimination. So then you get different code outputs.
Potentially, yeah. I'm pretty sure that, depending on some ordering decisions or choices, and we'll actually see some different choices here, you may get different code. But because because this is sound, and semantics preserving, it won't change the functional behavior of the program. The same inputs will give you the same outputs. But yeah, it just reflects the fact that there are many ways to rewrite the same program. You can have one algorithm, same input and output specification, lots and lots of different ways to express it. All right, so let's use this available expressions analysis to do our common sub-expression elimination. So here we see, remember, so just recall I won't go back, but recall what our common sub-expression elimination looks like. If we have V1 equals some expression and V2 equals some expression, we can replace V2 equals expression with V2 equals V1. So here we notice from our set of available expressions, which now is conveniently, on this statement, we see that there is yet indeed another variable that equals B. We don't have to even think about whether this variable is reassigned or not because we did our available expressions program analysis. And we can just replace B with A, replace the right-hand side with the variable that already computed that expression. Similarly, when we get to A plus B here, we can look in our set of available expressions and see that D equals A plus B and do the replacement, eliminate that common sub-expression. And again, we see B here. So notice that there are actually two possible things we could replace with this. So, there's multiple ways to generate this final code. In this case, in this example, it chose the first one. It chose A equals B. I don't know if there may be some difference to doing that. There may be some heuristic there that I'm unaware of. Here we see A and B again. So we see that E equals A plus B is, is that right? Oh, yeah. So we see that E equals A plus B, same expression. We can replace that with E. And finally, that's using available expressions analysis to actually do the steps of our common sub-expression elimination. So questions?
If you go back to the one here, the next slide,
Oh, here?
the next slide.
Oh, next slide, this one.
Yeah.
Oh, yeah.
So now A equals B, and that means A and B are the same.
Right.
So couldn't you just do like 2A and do a 2 shift left logic on A?
Oh, you mean here?
Yeah.
Yeah, that's true. So I think the copy propagation would make that possible. So if you had copy propagation, B would be replaced by A, and then you'd have a different, an arith. Well, I won't go to that slide, but you would do these strength reductions, I think. Is that right? Yeah, there's a name for this where you replace operations with equivalent operations. So if you've got, actually multiplication is probably slower. Oh yeah, but right, it would be multiplication by 2. So yeah, you could shift. So I'm sure compilers do that, where if they see the same values added together, then you shift them. And there are other analyses where you can actually prove that two values may be the same, even if it's not the same variable. There may be some like aliasing analysis that you can do. But yes, you're absolutely right. You can do these kinds of optimizations to the arithmetic as well, for sure. Other questions? Questions? Okay. All right, so live variable analysis. So the analysis that helps us do this dead code elimination. So remember, dead code was a variable's defined, but it's never used anywhere else. So we want to eliminate that operation. And you can imagine that we as humans could sort of easily pick that out. But how do we design an analysis that will do that in a way that is true for every possible input to the program, a sound way? So the definition of a live variable is it's live at a point in the program if its value will be read before it's written again. So if you got a equals 2 and a equals 3, then the first definition of a is not live when you redefine it. So in dead code elimination, just like we did with common subexpression elimination, it works by computing the liveness for each variable at each program point, and then just eliminating assignments to variables that aren't live after that program point. Okay, so to do this, we actually traverse the block in reverse order. We start from the bottom. We start from the known, whatever known live variables we have at the bottom of the block. Because remember, in a large CFG, if we're only doing local optimization on a single block, that variable may be used somewhere, much later in the program. So we kind of assume that in our basic block, we know which variables are live at the end of the block. And then we work backwards in the statements. And this kind of makes sense because we're trying to start from where they were used and figure out where they're still alive until they're, the previous definition of that variable. I did not say that well, but we'll see an example. So basically, if we see a statement like a equals b plus b, just before that statement, a is not alive because it was reassigned, right? But after the statement, it's still alive because it was assigned, and if it was live at the end of the block, then it's still live when it's being reassigned. That's where the liveness starts. Just before the statement, both B and C are alive. So before this statement, in order for this statement to work, B and C must have been, held in memory or in some register that must have been live before that. This is the two kind of updates that happen when we do this live analysis. If we see a statement, then whatever was before it, that definition is killed. That definition of A is killed, and that variable, you don't need to keep track of this value of this variable before it. And for B and C, this statement tells us that B and C are live at this program point. So as we continue going backwards through these expressions, we need to keep track of the fact that B and C are still alive at this point. Okay, so what if we have A equals A plus B? What does that mean? Yeah. A has to be live for sure. Yeah, and even though it's being updated, A is still live. A has to be live, and then the new value of A, it has a new value that could potentially be used later in the program, so still live. Okay, let's look at an example of it, and then let's see how it goes. So let's just assume, just when we get to global analysis, we'll see why this is the case, but let's just assume that B and D are live after we leave this block. Those variables are already live. So let's work backwards, computing the live variables at each program point. So because E is used here, we know that E must be live just before this assignment statement, right? It's got to be. And this does not affect B or D at all. So B and D are still live at this program point. They're live at the end of this block, so they must still be live before F equals E. Similarly, so similarly, A is also live before D equals A. But notice that because D is reassigned here, we know that D is not live before this point. Because even if it were defined, like here it was defined here at D, because it's reassigned before its old value is used, we can assume that the variable is not live in this point. Okay, so let's see how this update process preserves that information. So now we've seen D equals A. We remove that from our list of live variables, and we add A to the list of live variables, because this is the first point where A, or this is actually the last point A is used in our program. but it's the first time we encounter A in our reverse analysis. With E equals D, we have something similar happening, where E is evicted from this set of live variables because it's been reassigned, and D is added again because it's the right-hand side of some assignment statement. Okay, so who can tell me what the next set of live variables is going to be when we see D equals A plus B? Yeah. Just the set containing A and B. So why is this? So D gets evicted because D was assigned at this point. So we know that the program point just before it could not have D as a live variable. A and B were already live, so they're still live at this point. And C, so notice here that C was not even live in our live set, so nothing changes. This C is obviously going to be dead code. A and B are still live here, and then finally, just before A is assigned, that kind of kills the liveness of A, and we can conclude that B was live when we entered this basic block, because it's the only, if you just look at the assignments, B was never assigned. So it makes sense that B is still live at this point. So questions on this? Oh yeah. It could be an input. So I'm kind of just assuming that this is some basic block in a bigger control flow graph. These may be returned from the program. They may be printed out. It's kind of interesting question is like, what are the ultimate inputs and what are the ultimate outputs of the program? And they're, if you're only thinking intra-procedurally within the function, that's the parameters in and the return values, and any potential function calls you make to functions that do its own outputs. But if you think about the whole program, it's like the reading from the operating system and writing from the operating system, or writing to a file. So those are like the ultimate inputs and outputs of the program. Without that, the program is like always constant. You always have to define the values. So ultimately, these values are going to be the sources and sinks, or the inputs from the file system or from the operating system, or outputs to the file system, outputs from the operating system, outputs to the network library. And in static analysis, you just kind of define the libraries that mean input and output when you do these kinds of analyses, like interprocedurally. Yeah.
After building it from bottom up, when we're looking from top down, I just want to make sure I'm understanding this.
Sure.
Everything in the brackets this is a variable that at some point in the future is going to be used in the code, right?
Yes, from that point, yeah. So you're saying, so say it one more time. So you're saying
the values in the brackets are something where this variable is going to end up getting used at some point.
Exactly. At this program point, we have to assume that at some program point after it, it's going to be used. We don't know what it is.
And so the reason D just got dropped off is because essentially that first instance of D and that second instance of D are two different things, right?
Yeah, exactly. So, and because D is never, D is used here. Wait, you mean where is D dropped off? Here?
That one.
Yeah, because D is used here, but it's redefined here. So if we think of this as like the program point just before the assignment of D, then D is not live at this point because it's just about to be redefined. Does that make sense?
If we had the line A equals A plus B, A would show up in the live thing at that point, though, right?
At this point, if we had A equals A plus B here,
yeah,
A is already live.
Yeah. So A.
Oh, you mean after it? Yeah. That was like this little tricky question here. What if we have A equals A plus B? And I guess there's no example here of that. But yeah, it would essentially evict itself and then add itself back in. Because this is not like what's the memory location of the variable or what's its precise value. It's just, is that symbol going to be used at some point in the future? So this is the kind of tricky part about static analysis, is that it's defined, it's proving some specific property about the program, but it's not necessarily like every possible runtime value. There's some abstraction going on. So in this case, the abstraction is like program symbols. So even though in some sense it's a different variable maybe, or a different value, for our live analysis, we don't really care about that. All we care about is whether that variable is going to be used at some point in the future. That's all we care about. So abstracting away all the other facts about that variable in the program. Does that make sense? All right, so let's do the dead code elimination for this. All right, so dead code elimination. Okay, oops. Dead code elimination can also work backwards here. So what is the first thing that will be eliminated? So here we see that B and D are live after F equals E. So what does that tell us about F equals E? It's dead. Yeah, it's dead because we know that because of our live variable set, we know that F isn't going to be used anyway. So we can just eliminate it without changing the meaning of the program. Yeah. Yeah, just assume B and D are given. Assume that this is the exit of a control flow block. So just like you asked before, ultimately these are going to be going towards whatever you define your program outs to be. Maybe program outputs to be. Maybe they're written to a file. Maybe they're going to print F. And if you're doing a static analysis that actually, where you need to know the ultimate output, like say you're doing a security analysis and you're making sure a person's location is never being written to disk, for instance, then you need to, for a static analysis, you would define what you mean by the output. So maybe that's the file system library, maybe that's the networking library, maybe that's writing out to the console, for instance. And if you trace all of these assignments through the whole program, you can start from those outputs and then work your way backwards and do effectively this live variable analysis and see is that person's location ever being could that ever go to the could it ever go to the internet or to some file? Okay, so what about in this statement here? B, D, and E are live after we say D equals A. So is D equals A dead code or not dead code? Not dead code, because D is live after this assignment. Oops. Oh, okay. I just gave the answer away. But what about E equals D? It's still live because E is in the live set. D is still live because D is in the live set. What about C? C is not in the live set, so dead code. A is still in the live set, so not dead code. Questions on this? Yeah. Union all of these sets together? Oh, that's actually a really good question. I think it'd still be right. You just wouldn't eliminate as much stuff. Actually, you would in this case, actually. Never mind. So that would work in this case. I think it would be sound because you're further over approximating. I mean, you could just say every variable is live everywhere all the time, and that would be sound. For this purpose, for dead code elimination, it would be sound. But yeah, in some sense, this is like trying to approximate the program a little bit more than just assuming everything is live. In some sense, you can think of that. Yeah.
Would the compiler run through this more than once to check if these changes are enough for you to mutate?
Yes. Yeah, it would. And in fact, if we reapply these live analyses and dead code elimination again, I guess this is why you're asking. So remember, where was it? Yeah, B and D was our assumed live variables. Maybe they're being written. Maybe there's printf B, printf D, or they're written to a file. D is still live because it's in the D is this. We don't eliminate. Anyway, D is still live here, but because D is being assigned, D is not in the live set before it. A gets added to the live set before it because it's being used. E was never in the set, so it can't be removed. D is being used here, so now we add it to the set. D is being assigned, so we remove it from the set. A and B are still used. We keep them in the set. And then B is still, is still live before A equals B. So we can do this live analysis again, and then, as you suggested, reapply this dead code elimination. So D is live after this assignment, so we don't eliminate it. E is not live after this assignment, so we can eliminate that. D is live, so we can't eliminate it. And voila, we can do this yet again. We know that B and D are live here. That's what's given to us. D is killed and A is added. Nothing is killed, A and B are still added, blah, 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 blah. We can do dead code elimination one more time to show that, A and B were found not to be live after this assignment. So D equals A plus B is also dead code. And that leaves us with, very, very simple assignment. Something that, is kind of unintuitive, right? Like if you were to look at the code, you'd be like, oh yeah, I'm not going to sit there and try to figure out all the assignment dependencies. Let a compiler do it. So that's the power of this live variable analysis.
And then just from other things you mentioned, that could be simplified to just D equals B.
Oh yeah, that's right. If you did the copy, yeah, right. The copy propagation. Yeah, or no, yeah. So common sub-expression elimination. Okay, so as someone else asked, can you just sort of combine these together? And you certainly can. So we know at this point that we already know at this point that F is dead. So we just eliminate it. There's nothing to update in our live analysis. D is live, so we can't eliminate it. We update our live set. We see that E is not in our live set, so we can eliminate it. We see that D is not in our live set also, so we can eliminate it. We see that C, again, is not in our live set, so we eliminate it, leaving us with the same thing, A equals B and D equals A. Okay, so that actually, I'm a minute over, so sorry about that. So next time we'll actually make this a little more formal and then talk about global optimization. So have a good night, and I'll talk to you next time.